Hi, this is Khayah Brookes, and today I'm chatting with Noah Iliinsky, who has some questions about machine learning that we're going to answer. Hi, Noah.
Hi, Khayah. I'm glad to be here. My first question for you today is a vocabulary word question. What is a hyperparameter?
That's a cool question. Okay, so in AI, the parameters of a model are the properties or quantities that an algorithm learns through training. So it's the actual output of a calculation. For instance, if your algorithm is take the average of a set of numbers, the average itself is the learned parameter. But if you have a more sophisticated algorithm, like taking a weighted average, the result is still the parameter, but the weights themselves are the hyperparameters.
Okay.
So those can either be assigned manually or adjusted through a process called tuning until the output meets your desired standard of quality.
Okay, that makes sense. So the hyperparameters are assumptions or preconceptions, and the parameters are the things you learn based on those assumptions.
That's a really good way of it. Yeah.
Awesome. How do you decide what hyperparameters to use?
There are two basic approaches to finding a good set of hyperparameters. One is validation and the other is tuning. You can use one or the other or both. Validation is how you find the right general setup to get good results, and tuning is how you dial things in.
Okay.
To validate a model, you sample the configuration space, probably by searching it randomly, and build several models with different sets of hyperparameters. Then you use data that was held out from the training set to test the performance of each of those.
Okay, so validation lets you sample different hyperparameters to choose good ones. So what's the configuration space?
So the configuration space is made up of all the possible settings for the hyperparameters. So a simple linear model like fitting y equals mx plus b has a two-dimensional configuration space, m and b.
Okay.
If you're building a model that has three hyperparameters, you're working in a three-dimensional configuration space.
Okay, so the configuration space is like all the ingredients and all the possible proportions when you're baking a cake.
Yeah, that's totally, yeah.
Got it. So why would you search that space randomly?
Oh, that's a really good question. There are usually two main approaches to choosing hyperparameters. One is to do a grid search, and the other is to do a random search. If you do a grid search, you define a range of possible values for each hyperparameter, and then you build a model that features combinations of hyperparameters that are evenly spaced in their respective ranges. But this method guarantees two things. One is there's a lot of ground that you never cover, which is to say everything that's between the tick marks on your grid, you just never even look there. And there are a lot of values that are measured over and over. So if you search a grid that has like 4 values for each dimension, and you have a 2D space, you're going to check 16 possible combinations of hyperparameters, but you're checking the same values 4 times every time.
Got it. Okay.
So the process of building a grid itself actually bakes a lot of assumptions into the possibilities that are ever considered.
So what about a random search?
Yeah, so a random search is wonderful. It chooses different sets of hyperparameters to train candidate models. But instead of starting off with everything on a grid, you initialize the values randomly within the range. So you can literally imagine, like, again, if you have a 2D configuration space, if you threw a handful of pennies on, and those would be your starting conditions. But when you had that 4x4 grid, when you checked 16 possible things, but you checked each of them 4 times, by contrast, if you throw your 16 pennies on the grid and they land randomly, you're probably going to sample 16 different values for each of the dimension in the same number of calculations.
Okay.
So this means that you can build a much richer map of the configuration space in the same amount of time. The enhanced view that comes from searching randomly means you're less likely to end up choosing a simple local maximum if there are better optima available for your purposes. And this is kind of an interesting random fact, but the proof that a random search of a configuration space is the best way to go was only developed in 2012. So that's just one example of the fundamental and powerful methods that AI scientists are discovering every day. Proofs like this save time and save money for practical applications. And that in turn makes more innovative and more creative work possible.
Super cool. That answers my questions.
Awesome. I'm so glad it does. Thanks so much for asking, Noah.
Thanks, Khayah.